Is that good?
Meeting?
Yeah, great. Okay, so it's a pleasure to have Andreas Helset here for the last talk of the session, and he's going to tell us about geometric soft theorems.
Okay, yeah, thank you for giving me the opportunity to talk. So I'm going to talk about geometric soft theorem. It's a recent paper I wrote with my collaborators Cliff Chang and Julio Parmartinez, also at Caltech. Yeah, so throughout the talk, we'll try to explain what I mean about geometric soft theorem. So it's about the soft limit of scattering amplitudes. And we can see that this is related to some geometry. But it's not a geometry in space-time, but it's a geometry in field space. So we'll define those concepts as we go along. But first, we can reflect on this conference as a whole. So we had QCD meets gravity, and there's been a lot of interesting talks about both gravity and QCD, which is not surprising because both gravity and gauge theory have very special properties. They have interesting double copy features. They also have universal soft theorems. So there's a lot to discuss. But there's also other theories which exhibit some of the similar properties, namely scalar theories. Like, for example, nonlinear signal model also has double copy features and universal soft theorems. So with that in mind, I'll be not mentioning gauge theory or gravity for the rest of the talk and only focusing on scalars for now and seeing what's special about the nonlinear signal model and whether some of these properties can be generalized to other sets of theories. So particularly the soft theorems we'll be diving into. So instead of just looking at the nonlinear signal model, let's just look at the general theory of scalars. So you can write down a Lagrangian with some set of scalars. They will be labeled by these phi capital I's. So the I is, I will be referring as a flavor index, but it can either have some symmetry or just no symmetry at all. So if you have like just a bunch of random scalars, you just group them as like some multiple of capital phi capital I, and you can just write down all the terms in your Lagrangian. So, and we'll group them by derivatives. So all the derivatives or the terms with no derivatives go into the potential. They could be the normal phi cubed, phi to the 4, and also high derivative terms or high dimensional terms there. And all the terms with two derivatives, we'll put in the form that's similar to the kinetic term. This is this d mu phi connected with this gij function in front. And all the rest, like high derivative terms, will be chucked into these dots. So what's very important for this talk will be this function in front, this gij. And this can be viewed as a metric, but it's not a metric in space-time, but it's a metric in field space. So it's some manifold where your coordinates are not x, but it's the field themselves. And this gij is like a 2-index object. It's symmetric, and we will see it has all the properties of a metric. And in this manifold, like in GER, what's very important is that you can always change coordinates, and the physics is invariant. And what this corresponds to in our setup is that you can always change your fields. So you can do field definitions, and the physics should remain unchanged. So let's just try to do a field definition. So we can start with our fields, and we can redefine them with some other function, var phi here. If you do that, you will see that if you take the partial derivative of this equation, you end up with a partial derivative of phi times some function in front. This is precisely a vector transformation. So the partial derivatives of the scalars will transform as a vector under field definitions. And because of that, in the kinetic term, we had two partial derivatives. So the metric in front will transform as a 2-index tensor, which is precisely the transformation of a metric. Okay, so far so good. And But in the end, we will like to talk about scattering amplitudes and not some manipulations in the Lagrangian. So let's just go through the steps of going from the Lagrangian to a scattering amplitude. So first, we have to expand around some vacuum, V. So all your couplings in the Lagrangian will depend on this, these vacuum V here. And at that vacuum, we can always canonically normalize the kinetic term. That just corresponds to like picking some tetrads, which flattens the metric at that point. So these E, I, capital I, lowercase I, will be the tetrad functions. So they toggle between flavor eigenstates and mass eigenstates. And you also have the freedom of diagonalizing the mass matrix in this way. We see that this tetrad also shows up as the overlap between the mass eigenstates and the flavor scalar fields. That's the EIJ showing up there as well. And then we can go from using the normal LSZ reduction formula to like the scattering amplitudes to correlation functions. So the scattering amplitudes will have these lowercase flavor indices here, while the correlation functions will be built from the fields with capital flavor indices here. And the way to toggle between these those indices is precisely these tetrad functions. The tetrad function shows up in the LSZ reduction formula as simply the wave function normalization factors, which is kind of like a trivial but cute result, I think. So like if you're confused about like the initial starting point and the things we show in amplitudes, it's simply these tetrads that's being used to contract or replace these indices here. Okay, so now we have like worked our way down from starting with some Lagrangian and calculating everything down to an amplitude. Let's just get some intuition of what to expect in the amplitudes. So let's focus on two derivative terms, the term with the metric and the kinetic term, and see what the scattering amplitudes look like here. So the first one will be at 4 points, and that's 4 flavor indices, like I1 to 4. And it's some kind of milestone variables multiplied by a tensor structure. And this tensor structure is not some arbitrary thing, but it's very precisely the Riemann curvature tensor derived from the field space metric we started with. So you can just like take any GR textbook, find an expression for Christoffel and Riemann, and just plug in the initial metric and calculate the curvature in the usual way. And that's the coefficient that shows up in this 4-point scattering amplitudes with these particular indices. While if you go to 5 points, now we have 5 particles, we have like 1 extra index. So we need 1 extra index in our tensor structure. And it turns out that the coefficients of all these Mandelstones will be a covariant derivative acting on the Riemann curvatures. So this is just 2 examples for a more general point that all the scattering amplitudes will depend on geometric invariance. And just to emphasize that all these R's and covariant derivatives of R's are respect to the vacuum expectation value of those couplings. So you can keep the vacuum expectation value general, and then you take these derivatives. And that's the coupling that shows up in the end. Okay, so with that in mind, we have all the ingredients to just state the new soft theorem. And the soft theorem will be on this form. So start with an m+1 scattering amplitude, pick a massless leg, and send its momentum to 0. So here, Q goes to 0 for index I. And what you will end up with on the right side is, in general, something that's non-zero, but it's simply 2 terms. So if we ignore the last term for now, it's simply the covariant derivative acting on the lower point amplitude. And it's a covariant derivative in the direction of the soft limit. So you can view this as like a shift of the VEV of the soft particle. So you shift all the couplings and all the internal propagators in your amplitude. So, but what's the second term then? It looks a bit more complicated, but it's not really that much more complicated, because you can view this as not a variation of the amplitude, but a variation of all the external propagators in your amplitude. So before you amputate all the external propagators, you take this variation of the mass, which will be the covariant derivative of this Vij, and then you amputate. So because this variation like creates like a double pole, like a single pole is left over at the end. So it's really just like compactly saying that the soft limit of n+1 particle amplitude just is the variation of the amplitude and the variation of all the external legs. Okay, so is this true? Let's see in some examples whether this actually makes sense or not. So we can go back to the example of two derivatives to know we don't have any potential, so we can just focus on the first term in the soft amplitude. So at 4 points, we had this Riemann curvature times a Mandelstam. And if we take particle force momentum to 0, we see that both these Mandelstams just vanish. So we get 0, which is consistent with the soft limit, which says that it should be the covariant derivative of the low point amplitude. In this case, it's 0. So both sides agree. But if we go to the next point, like 5 particles, we start with the 5 particle amplitude here. We take particle 5's momentum soft. And I've written it in a very suggestive way, where if you look at all the Mandelstams in the top line here, they all depend on particle 5, so they all vanish. While the second line has 2 terms, and they don't vanish. So we get a non-zero result. And if you focus on in the second line, the index on second line of the covariant derivative is all the index of particle 5. So we can put that on the outside, and we see that the thing in the brackets on the last line is nothing but the 4-point amplitude. So we have the covariant derivative of the 4-point amplitude, which is what soft theorem says. So you can continue this at 6 point and 7 points, where there will be more and more complicated structures. There will be poles which collapse and combine up with the contact terms, but it all agrees with simply being the covariant derivative of the low point amplitude. So what about the other term in the soft limit, in the soft theorem? So we had this covariant, and then we had also this potential term with some propagators. So if you look at a theory with only a potential, we see both in play. So for example, the 4 point of a theory with only a potential, it has a contact term, this V with 4 indices, and it has some factorization tunnels from the cubic interactions. And we can then recognize each of these 2 terms as coming from 2 parts of the soft theorem. The first one will be just the covariant derivative of the low point amplitude, so nabla times A3. Well, all these poles, which do not go away, they're there. They're simply coming from the variation of all the external legs, or the second term in the soft theorem, which has these poles explicitly. So even here, see, things group up nicely to adhere to the soft theorem. And you can do more complicated things with combining a potential and 2 derivatives with high derivative terms and check explicitly whether things match. So what about pions? So we started out saying that the nonlinear sigma model, the theory of pions, was special. So it has double copy and has a universal soft theorem. And that soft theorem says it should vanish when you take any particle soft, then the amplitude should be 0, which is also known as Adler 0. But in general, we have this non-zero soft theorem. So how does these 2 things combine up? Let's just look at the n+1 amplitude, take a soft limit, we get the covariant derivative acting on the low point amplitude. And then we force that this should be 0. And this constraint imposes some constraints on the geometry. It in particular says that all the covariant derivatives acting on R, on the curvature, should vanish. This is a very specific geometry known as with a covariant constant curvature. So the covariant derivative of the curvature is 0. The curvature itself is non-zero, but the nabla curvature is 0. And this corresponds to a symmetric space. And also it's like a symmetric coset. So all the symmetric cosets have this adder 0, which corresponds to a covariant constant curvature, which gives a 0 in the soft limit. So it all agrees, but it gives a different perspective to known results. But it also gives a new perspective for new results as well. So let's see if we can find other examples where it's non-zero, but we still have Goldstone bosons. So if we have a theory with some symmetry, right? And just like check the potential for now. So we only have like a non-symmetry in this form, so you can shift phi by some k here, and the action has to be invariant. What this corresponds to is that this shift is actually a Killian vector. So it's an isometry of your manifold. So it keeps your manifold invariant when you do this shift. And because you don't have this Killian vector, what you can do in the soft theorem is you can contract this Killian vector into the amplitude. So you start with the n+1 amplitude here. You want to take the leg of particle I soft. And before that, you just contract it with this Killian vector in that direction. And then we can use that, we get the soft limit produces this covariant derivative. Now it's contracted with against the Killian vector here. And because this is a symmetry of the Lagrangian, it's also symmetry of the amplitude, meaning that the lead derivative along the Killian vector of the amplitude vanishes. And that allows you to swap where the covariant derivative is acting. So instead of acting on the amplitude, it can be acting on the Killian vector itself. So you just get like this prefactor like nav like k, and then you sum over all the legs in the amplitude, the low point amplitude. This is actually like a generic version of a new soft theorem that was found last year. So it's like a non-zero soft theorem for Goldstone bosons. It's rather interesting. Okay, and just to end on something else. So when we have this soft theorem, we can just turn the crank. So instead of taking one particle soft, we can take two particle soft. We can do it in different ways. So if we take first one particle soft and then a second particle soft, we'll just get more covariant derivatives as before. So it's not so interesting. But if we take two particles soft at the same time, then we get something interesting. And this is also there even for pions. So the pion vanishes when you take a single particle soft. But if you take two particles soft at the same time, it's non-zero. And we can then generalize this result to a generic theory where the result is just if you take two particles I and B soft, you get two terms. One is sort of like the expected term. This is just the symmetrized covariant derivatives acting on the low point amplitude. And then there's the other term, which is more like the antisymmetric combination corresponding to low point amplitude, the Riemann curvature, and some kinematics that compensate for the antisymmetry in the curvature. So these two things combine up to be the full double soft theorem, where it was only the first term that was non-zero for pions. Right. And you can go on. We also have a triple soft theorem. So you just like redo the analysis, but now we do the three. And you get some result. It's more complicated, so I didn't put it in here. but it's more of the same. You get more R's, more covariant derivatives, and some different kinematic structure. And you can, in principle, just keep on going with more and more particles. Well, the triple soft theorem, there's no analog for pions because it's just zero. Well, here we get a non-zero result. So I don't want to keep people waiting for lunch. So let me just summarize and with some remarks. So we derived new universal soft theorem for any theory of scalars. It's really important that it's really general. Like it's every scalar theory you can write in this way, and you get a soft theorem. And the take-home messages are a couple. So for me, at least, this highlights why geometry, this field space geometry, is important for scaling amplitudes. Like this geometry, like without it, you wouldn't see where these soft theorems are coming from. And what's kind of more surprising is that instead of like focusing in on one specific theory, which has like very special properties, we're zooming out to the general set of all theories. And this zooming out, instead of making it more complicated, makes it easier because it reveals the structure. It reveals the structure of this geometry. And in particular, it's saying that soft theorems, they're not special, but they're general. They're general features of every scalar theory. So one might wonder whether this is a coincidence or it's like a lesson that could be true for other properties as well. So maybe it's useful to zoom out and look for generalizations of other properties as well that we're studying. So with that, I will just thank you for your attention.
Thank you, Andreas, for a very nice talk. I think we have time to take questions. Plenty, in fact.
Well, can you comment on trying to extend these ideas to gauge theories with issues on?
Yeah, yes. So there are a couple of things we can extend this with. One thing we can do is to extend it, like adding gauge theories in the theory, but looking at the scalars themselves. And I think we basically know how to do it. There's just more of the same. It's more of the geometry, more of the structure that's there. But yeah, we're working on like finalizing something on that as well.
What about external gauge particles? What the or why isn't that straightforward? Or
it's not that straightforward.
But what is the issue that?
Well, so it's like the question, like, what's the geometry when you have gauge theories? And the way to attack it is to say, okay, now we can, the geometry relies on field definitions. So let's allow for field definitions for the gauge theories as well. And then we can find what's the invariant combinations under those transformations. So in this case, it was the curvature, or it was the covariant derivatives of the potential. When you have gauge theories, there are other structures which are invariant under both scalar and gauge field definitions. And those are the things that show up in amplitudes. So you sort of like do a two-part thing. You can look for things in the amplitude, see what's there, and try to like extract that from the Lagrangian, or you can do field definition in the Lagrangian to combine up things that's invariant. It's not obvious at all. There are issues, there are technical issues, but in principle, it should be doable because you're allowed to do field definitions.
Yeah, thanks. Very nice talk. I have a question about the amplitudes with vanishing soft limits. So it was observed that despite the soft limit vanishes, the leading term in the small parameter that you send to zero can be interpreted in many cases as amplitudes in extended theories,
yes,
like extra scalars. So would that fit into the story?
Yeah, that's a really great question. So it's really like, what's the coefficient of zero here? And this soft theorem is only for the leading in Q, like the constant in Q part. It doesn't say what the linear in Q coefficient is. There would be like the subleading correction to this geometry. I don't know what the expression will look like in general, but I would be surprised if it's unrelated to this. I think it should be somehow interpreted in some geometric way, but it's gotta be more complicated. So in particular, we have a proof for the soft theorem, and you can try to rerun the proof, just add like keeping corrections to order Q as well. But it gets more complicated because there's a lot more terms in the you have to care about.
Yeah, because these vanishing terms have more particles, right? It's like coupled to some other theories. So
Yeah.
I would wonder how does it arise in your story?
Yeah, I don't know, but it's really interesting to look at. Yeah, so definitely something to look at.
Yeah. Do you have any vision of how this would generalize to one loop or higher loop corrections?
Right. So all the examples that we checked are tree-level examples, but in the proof that we have in the paper, if you ignore the potential, I don't see what's different from tree-level and one loop. I don't see where the loop kills you. So I would expect it to be valid. If you ignore the potential, I would think it should be valid at loop level as well, because it's really similar to the Adler zero proof, which is, yeah, but we haven't checked anything beyond tree level.
Well, so that in the gauge case, there should be some subtlety there, because it's not going to be so trivial.
Oh, gauge, I don't know anything about loops and gauge theory at this point.
Thanks for the nice talk. So my question is probably similar to Yara. So you said a little bit more on, say, if you have a couple series like AI.
Yes.
Yeah.
So there were these high derivative terms, which is like implicit in the dots. So it does work whenever you have these high derivative terms as well. But in the theories you're mentioning, BI, especially Gaussian, they all like vanish in the soft limit because they're derivatively coupled. And then they have like enhanced soft limits as well. But since we're like restricted to only leading order, we can't see beyond leading order in Q. So I'm not sure what's the geometric interpretation of those soft theorems, but that would also be interesting to look into.
There's also a question from the chat by Carlos, who's asking for the full Volkov 73 reference.
Sorry, I didn't catch that.
Sorry, Carlos from the
Volkov reference. It's I can send it to you, or you can look for version 2. It's not in the version 1, unfortunately, because we were contacted by someone saying, "Oh, by the way, do you have this?" It was in some Soviet journal that was in the library at Caltech. It wasn't online, so I'm not sure how helpful it will be. But yeah, I can send it to you if you want.
Any more questions? Okay, great. Then let's thank Andreas again. And this wraps up our second session today. We'll have a pretty exactly 1 hour break for lunch or dinner, and we'll reconvene, I think, at 1 p.m. local time, whatever that is.